Okay.
Okay, sure. Please tell me when to start, and I will start.
Yeah. Thank you. Okay, so I think we can start with the introduction now. So, okay. Yeah, so good afternoon, everyone. And today, the first speaker for our afternoon special session is Ms. Tanaya. So, to introduce her, it is my great pleasure to introduce Ms. Tanaya, who is currently pursuing her PhD at Harish Chand Research Institute, HRI. Her research interests include theoretical condensed matter and quantum information. And today she'll be talking on her recent research work on the title Optimal Quantum Resource Generation by Coupled Transmons Immersed in a Markovian Map. So, Ms. Ray, the stage is yours.
Thank you for the kind introduction, and good afternoon, everyone. So, first of all, I'd like to thank the organizers for this platform to present my work and communicate to other researchers. So, the topic of my talk is quantum resource generation by coupled transmons in Markovian baths. So, the outline of my talk is shown that first I'd like to discuss the transmon systems briefly and the circuit diagrams. And then I'd like to describe the coupled transmon system as a part of a larger circuit and environment, and then quantum resources in such systems, and then the resource generating capacity, and the estimation of the most favorable initial state. Then I'd like to discuss the sustainability of such resources depending on the interaction strength of the subsystems, and then how the entanglement dynamics of a non-Markovian system can be mimicked by such a system, and then I'll conclude my talk. So first of all, why should we be care about transmon systems. So what's special about transmons is that it provides us with longer decoherence times. And nowadays, I mean, on the large companies, the IBM, Google, they're building prototypes of quantum computers by these systems to, I mean, implement the quantum computing protocols. And then the next topic, I mean, I'd like to discuss the transmon circuits in briefs. So the circuit diagrams shows the Cooper pair box, which is coupled to the ground or another superconducting island by a large capacitance. So the Hamiltonian is basically that of very similar to Josephson junctions, because the Cooper pair box, I mean, in the Cooper pair box in the diagram, the inductance comes from the nonlinear Josephson junction. So that is why the Hamiltonian looks like this. And where Ng is the gate voltage, and this charge operator in cap, this denotes the charge difference in units of Cooper pairs between the junctions. And this phi is the phase difference across the junction. So the Josephson energy is given by this EJ and the capacitance energy. And to make a transmon, this CS, the shunt capacitance, is much, much larger than the capacitance in the Cooper pair box. So, I mean, if we quantize the circuit, this is how we transform the circuit quantization with this transformation of operators, this n cap and phi cap into A and A decay. So in the transmon circuit, I mean, there are two factors to be taken care of. One is the anharmonicity of the system, and another is the gate charge sensitivity of the system. So the anharmonicity, I mean, if we do the computation, and I mean, we can see that if we increase the capacitance energy EC, so then the anharmonicity of the system increases, and which provides us with better control over the system. But if we increase EC too much, this charge sensitivity, this EM, so this sensitivity also increases. So this, so we cannot, I mean, we have to find a sweet spot between the EC and EJ. So this has, the people have found that the balance of EJ by EC equal to 100, that gives kind of a sweet spot between these two things. So this and we have solved the system with the explicitly correlated Gaussian technique, and one can also approximate this with a perturbation or variational approach or various techniques. So we have checked that those techniques gives comparable results. And if the system was a quantum harmonic oscillator, that is the inductance is linear, then the above picture, the number A picture, it would give the energy levels are denoted. But for the case of transmons, the picture B, that the more you increase the energy levels come closer. So the anharmonicity to first order in the capacitance energy, that is roughly equal to the capacitance energy of the system. So that means that this difference between this omega 01 and omega 12, this is easy, and then the omega 12 and the omega 23, that is also easy. If we take terms up to first order in EC. And since EC is a very small number, the first order approximation is a very good approximation. So then, we can couple two transmon system either by a capacitor or by inductive coupling. So here in this work, we consider the capacitive coupling scheme. So we couple these two transmons, by a small capacitor, and then we quantize the circuit. So that provides us with this Hamiltonian, this 4 ECI ni square minus CGI cos phi I, that is the individual transmon Hamiltonians, plus this 4 EC square CG by C1, C2, N1, N2. And next part is that we describe the coupled transmons as a part of a larger circuit and environment. So we have considered two bosonic baths coupled to the two transmon qutrits, and where the system bath coupling is very weak. And people have shown that given the decoherence times of the transmon system, considering up to 4 or 5 levels is enough for practical purposes. So in this work, we have considered up to 3 levels for both the transmons. So we have considered weak system bath coupling so that the bond Markov approximation is valid. And each of the local baths has infinite number of non-interacting oscillators. So the system bath interaction can be given by this HSB, and where this QIs represent the charge operators of the individual transmons in the units of a Cooper pair, and we express this in the basis of the global Hamiltonian of the system, so that they look like this Q1 and Q2. And so the total Hamiltonian of the system can be given by this H12, which gives us this individual transmon Hamiltonians plus the capacitively coupling interaction Hamiltonian term. We have tuned the interaction by a parameter gamma, and these BIs are the bath Hamiltonians, and the system bath interaction we just describes this. And now we can describe this by this master equation, where these dissipators are given by this expression, and the spectral functions are given and a second order Drude-Carter form we have considered, and these pi i's come from this Q1 and Q2, Q1 and Q2. Since the charge operators are the operators that couples the systems to the bath, so this pi i's comes from those charge operators expressed in the basis of the global Hamiltonian. So if we consider the quantum resources in such system, so first I'd like to define the measures I'm using in this work. So first comes the L1 norm of quantum coherence, and for an arbitrary d-dimensional quantum state, the quantum coherence, the L1 norm of quantum coherence is given by this form, which sums of the moduli of the off-diagonal elements in the density matrix. And in this work, we've normalized this coherence by the maximum L1 norm of quantum coherence in the system, which is given by this d square minus d by d. And so, for our system, the 2 qtrit system, so that is 1 by 8. So this is the measure of quantum coherence we have used. And we have for the bipartite entanglement, we have used the logarithmic negativity, and where the negativity is given by this, and the trace norm of any operator is given by this square root of lambda divided lambda, and we take that trace, and the logarithmic negativity comes from this logarithm of log base 2 of twice the negativity plus 1. And in our system, these are the parameters we have taken. So the Josephson energy and the capacitance energy of both of the transmons we keep 100, so that both the subsystems remains in the transmon regime. And this H cross gamma, that is capacitance energy by 5. So this denotes the coupling, the strength of the capacitive coupling between the two transmon qutrits. We have kept it very small. So EC is equal to 1 and EG is equal to 100. So this is 0.2. And the system of coupling parameter is a kappa, that is omega 01 by 5. That is the first ground state energy of each of the transmons. And we take 1/5 of that. And we have also taken smaller values. So to check that, I mean, if the smaller values change the system, and I mean, if the Markovian limit remains, we have checked, I mean, that it remains valid. I mean, we have taken it omega 01 by 20. The plots are for these values and this value. So, I mean, where omega 0, the ground state energy of each transmon circuit can be expressed in this √8 EJ form. And we have taken the bath temperature such that this beta H cross omega 01 remains 5. So to study the quantum resources in such transmon circuits, we first prepare the transmons in the ground states, and then we turn on the subsystem interactions, and we study the variation of the quantum resources. So we can see that if we, I mean, for the unitary dynamics of a closed system, so this is the nature of the entanglement remains oscillatory. But in the presence of Markovian bugs, both the coherence and the entanglement, they decay, but with an oscillating nature. And similarly, we have studied it for if the initial states are the first excited state, but those are also the states which have initially zero quantum resources in them. So for the unitary dynamics, they oscillate as we expect, and for the Markovian case, they do decay, but first they shoot up to a very high value from the zero resources, and then with an oscillating nature, they go down. So we have that motivates us that even if we start with a zero resource state, we can generate some resources in the system. I mean, just by letting the system evolve under certain conditions. So, I mean, how much quantum resources can we extract from such a system? So, and also, we can see that if we start from an initially entangled state, the system only decoheres. So we don't get any more advantage over the initial value. So next is the resource generating capacity, I mean, of such system, and we estimate the optimal initial state. So to quantify the such self-generated quantum resources, we have to take into account of two factors, that starting from the zero resource state, the zero entanglement state, how far the self-generated entanglement of the system can reach, the peak value, and over how much time the system can sustain such self-generated resource. So for this purpose, we have considered only the half peak value, I mean, up to the half peak value of such resources, so that if the system, I mean, the bipartite entanglement of the system, I mean, evolves in such a nature, we take only this is the peak value, this is the half peak value. So we take the time integration of only the regions in which the system has an entanglement in between the peak value and the half peak value. And this is the function of the initial state, as we have studied. So the system can generate, I mean, the entanglement dynamics can vary in various ways. So one is this, and another is that, I mean, it can keep oscillating and I mean, like these two values. So we have quantified the self-generated entanglement by this EOPT, which takes the maximum over these summation over this time integrals of this self-generated entanglement. So this Tn minus and Tn plus are these, suppose the starting and ending time points of the nth peak in the entanglement dynamics. So we have taken a sum over all such peaks. And the optimal state with the maximum resource generating capacity, that turns out to be rho is opt 0, this state. And for this optimal initial state, we have noticed that these two are not symmetry. These are rather closer to 1 than 0, and they are separable. And for the optimization procedure, we have only considered such separable states because, I mean, as we have shown previously, that if we start from an entanglement state, it only goes down, so that system does not generate any entanglement beyond its initial value. So that is why we have taken only the separable initial states, I mean, which have 0 quantum resources when you start, and then it generates entanglement within the system. So it is more like an information feed forward. The Markovian baths, I mean, that tries to decoher the system, but due to the presence of the non-local Hamiltonian, as if that term keeps feeding in some quantum resources in the system. So then comes the sustainability of such resources depending on the coupling strength of subsystems. So the subsystem interaction term looks like this. So what happens when you increase the interaction strength? So for the unitary dynamics, if we increase interaction strength, the maximum attainable entanglement of the system goes up almost linearly, and we have not taken values beyond this point because this expression, I mean, we can quantize such a capacitively coupled transmon circuit in the limit of this coupling capacitance is very, very less than equal to the individual circuit capacitances. So that is why we have limited our study in this region. And for this study and the subsequent study, we have started with the ground state of the system. So for very small values, the entanglement and coherence of the system goes like this. So we can see that not only the maximum attainable self-generated resource in the system increases, but the long time value increases as well. So the more we increase the strength of the non-local Hamiltonian, I mean, which couples the subsystems, the long time value increases. So for the Markovian baths, try to decoher the system, but the stronger the strength of the inter-system interaction, it is not the interaction strength between the system and the bath, I mean, which controls the Markovian or non-Markovian regime, but it is only the interaction between the subsystems. So as we increase that, I mean, as if that non-local term feeds some resource into the system. So that is why, I mean, we can see the increase in the resources. And I mean, if we take a slightly higher values within the limit, so that the circuit quantization still remains valid, we can see that the same nature follows. That we start with a zero resource quantum state, and the system bath coupling remains the same, but we just tune the subsystem coupling. So this gives us a potential increase in the decoherence time of the system, I mean, which can be practically useful for experimental purposes as well. So next, I'd like to describe that, I mean, how this system means the entanglement.
A couple of minutes left, so then we can
okay, sure,
some questions.
Sure, thank you. Okay, so in this paper, so they have described that this green line describes the entanglement dynamics of a system in presence of Markovian baths, and the red line, the non-Markovian bath case. So we can see that, I mean, though we have taken the Markovian bath, I mean, in our system, the dynamics of the resources is very similar to the non-Markovian case. This, I mean, as if there is some information feedback into the system very similar to the non-Markovian bath. So we see that in the system, in spite of using the Markovian local baths, the non-Markovian entanglement dynamics can be somewhat mimicked. So then I conclude my talk. So we can see that coupled transmons are practically realizable and useful, and the realistic ones will all, I mean, can almost never be isolated. So we have to take into account the environmental factors and the bath. And then we analyze the quantum resource generation in such system. And then we have shown that mimicking the non-Markovian entanglement dynamics can be mimicked in this Markovian limit with non-local system Hamiltonian in such system. And this is the paper that I focused on. And the team is this. And thank you.
Thank you, Ms. Ray, for your nice talk. So I would request the participants, if they have any questions, to unmute themselves and ask the question. Thank
you. Thank you for your talk. I have one clarification question. So, do you study decoherence level by computing quantum coherence parameter, that is impact of decoherence on off-diagonal elements of the density matrix?
Yes. I mean, for this coherence plots, we have, I mean, that you can see here. So we have taken the L1 norm of quantum coherence, so which sums up the off-diagonal terms, and then, I mean, to normalize it, we have divided it by A. So this measure we have used. So which sums up the moduli of the off-diagonal terms in the density matrix. So that is why we have used in this work.
So it means that if I have a Bell state which is in pure state, and then after decoherence it may become mixed state or
yes, and I mean, actually, if you can see that this picture, I mean, we can start with an initially entangled state, and then it will decoher just like this.
Thank you.
Okay, thank you. So should I stop sharing?
Okay, so if there are not any further questions, we would like to thank Ms. Tanaya for the very